Hi there, and welcome to our video on scientific methods. Our key ideas for this video are how can I think and act like a scientist, and how do scientists measure things? So our first question, how can I think and act like a scientist? There's a list of things we can do. We can identify problems, we can plan experiments, we can record observations, and correctly report data are just some of the most important science skills that we can utilize. And scientists approach problems by thinking logically. So we're going to logically think our way through these problems when we come across them or experience them. So thinking critically also is a useful tool to lead towards thinking logically. So critical thinking is defined as the ability and willingness to assess claims critically and to make judgments on the basis of objective and supported reasons. How about you just think logically about how stuff works, right? And how our answers come about. And scientists use scientific methods to kind of work through this critical thinking process to solve problems. So a scientific method is just a series of steps followed to solve problems, including collecting data, formulating a hypothesis, testing the hypothesis, and stating conclusions. The scientific methods are general description of scientific thinking rather than an exact path that scientists follow. So I've got a visual here that we'll look at. We're going to think of scientific methods as a circular process and not a set order of steps. So typically when we're working through a problem, we're going to start with an observation. So once we have made an observation about how something works, how it's changing, then we're going to go through and say, oh, we need to ask a question. So what's going on with this? How is it working the way it is? So we're asking a question, and at this point we might be searching the internet. We're searching Google, seeing if we can find an answer to that problem. If we can't find an answer, an exact answer to that problem, I'm then going to form a hypothesis. I'm going to say, all right, since this is the way it seems to be, I'm going to say, if I increase the temperature, then the plants will grow. So that might be an example of a hypothesis. I'm then going to maybe make more observations, or maybe I can test that hypothesis. So what I can do is set up an experiment, and I've got my independent variable. So if I want to test plant growth based on temperature, I'm changing the temperature. That's going to be my independent variable to what I change. And then my dependent variable, the plant growth, will be what I'm measuring. So I test the hypothesis, and then I look at those results. I see how they played out. What kind of results did I get? And then from there, I can draw some conclusions. Did the evidence, did the experiment that I ran through, did it support or not support the hypothesis? If there was support for the hypothesis, then I can do one of two things. I could communicate those results, but I'm probably also going to check to make sure those results were indeed good results. So I'm probably going to go back and test a hypothesis again. I'm going to run through it a couple more times, make sure I'm still getting the same results. If I were at my conclusions stage here and I found that the results didn't quite match or didn't quite fit, I would then go back and maybe test again and see if maybe I just had an error in something, my experiment, or I might change my hypothesis and form a new one. So maybe I need to test a new hypothesis. Maybe I say if the temperature is between this and this, then I see more sustained plant growth, but once it gets above this point, so if the temperature raises above this point, then I see stunt in growth, for example. Again, then I run back through this experimental process. So we test those hypotheses. So a hypothesis, we mentioned once before, a hypothesis is just a possible explanation or answer that can be tested. Scientists test a hypothesis by doing a controlled experiment. A controlled experiment is an experiment in which the variables that could affect the experiment are kept constant or controlled, except for the one we want to measure. And that one we want to measure is the dependent variable, right? And a variable is just a factor that changes in an experiment in order to test the hypothesis. We don't consider any test a failure. So anytime we run through an experiment, we get results. That results either support or disprove what it is that we wanted to test, but it's not a failure. So it's still useful. The result of every experiment can be used to revise the hypothesis or plan tests of a different variable. So maybe we just need to change it a little bit. And then if you're planning on going out and do your own research, you're going to publish your work to peer-reviewed journals, peer-reviewed research, and that's just research that's been reviewed by other scientists. So we could do that very easily in class by having other students review what our results were. So those would still be peer-reviewed. The other thing that I want to hit on in this section is units of measurement. So our other key point was, how do scientists measure things? So scientists use standard units of measure that together form the International System of Units, or SI. And we tend to use these SI units for consistency. So we use it here in science, they use them in England, they use them all over the world. We have 7 base units. So length, we use the meter. Mass is typically kilogram. In chemistry, this first semester we'll probably use the gram, so we'll use 1,000 less a kilogram. Time is measured in seconds. Temperature in kelvins. More often than not, we'll actually use Celsius instead of Kelvin. And these last 3 we probably won't worry about, but electric current, the amount of substance, and luminous intensity are also base units. But we're not going to worry about those last 3. Last thing I have here is a derived unit, and this is a combination of base units. For example, if I wanted to measure the density of a substance, I'm going to measure both the mass and the volume of that item. So some common SI units that I use. For length, I've got meter. We can also use kilometer, decimeter, centimeter, millimeter, micrometer, and nanometer for measuring length. So kilometer for something very long. A nanometer is something that we'd see at atomic level, so something extremely small. And volume, we use the cubic meter as the SI unit. Typically we'll see milliliters, but we can also see liters and cubic centimeters. And it turns out that 1 milliliter of water is equivalent to 1 cubic centimeter of water, which is also abbreviated cc. So in the medical field you'll see cc, which is the same as cubic centimeters. For measuring mass, we use the kilogram, and again in first semester we'll probably stick more with the gram measurement, and then we could measure smaller things using milligram. And then again in temperature we've got Kelvin, but we tend to use Celsius in science a lot more than we use Kelvin. Alright, on this next slide, SI prefixes for very large and very small measurements. These prefixes are multiples of 10, and these ones that are listed here are for larger measurements. So we use kilo, which is 1,000, mega, million, and giga is a billion. Some for smaller measurements. We've got deci, which is 1/10, centi, which is a hundredth, milli is a thousandth, micro is a millionth, nano is a billionth. And when we're measuring or using measurements to quantify our observations, length is just a measure of a straight line distance between 2 points. Mass is the measure of the amount of matter in an object, not the weight, so weight is different. Volume, a measure of the size of a body or region in three-dimensional space. And then the weight is a measure of gravity force exerted on an object. So one final thing I want to look at here, when I measure the volume of a solid object that has fixed sides and shape, well, for the cube, for example, I can measure the width, the length, and the height to get the volume of this cube. I could also, if this was an irregular object, like my little fish here, I could have a test tube that I filled with, say, 32 milliliters of water. When I drop my fish in there, the water level goes from 32 up to about 38. So what I can do is take 38 minus the 32 to give me the volume of this object, this irregular object. So 38 minus 32 gives me 6 milliliters. So this object that I have is 6 milliliters. One quick other note I want to make: when you're measuring the volume of a fluid in a glass test tube, we have to look at the bottom of the bubble. So that's the meniscus, and we have to look at the bottom, not the sides, but the bottom. So, thanks for listening.